Hello and welcome to this background slide video, and today we're looking at SI units, multipliers and engineering notation. Now, quick note on this, it goes way beyond what is required for the foundation, intermediate or advanced courses, although some elements of it you will need to broadly understand. But don't get bogged down in this, just use it as a general appreciation. And more detail, or the exact detail that you need, can be found in the RSGB books, or indeed videos that are specific to the foundation, intermediate or advanced course. So view this as background and don't get bogged down in it. So let's have a look at some units. System International d'Unité, and apologies for the pronunciation, is the most common form of measurement. It is used worldwide, and it is the modern evolution of the metric system. And other systems are still in use, for example, foot-pounds to measure torque. Other systems are predominantly used in, for example, the USA, which, although I believe NASA has recently transitioned completely to SI, up until recently it used a mix of units, which famously caused it some problems. So the SI system also has a system of multipliers. Why would we use multipliers? Well, we use it because the numbers that we deal with are often very large or very small. So we might talk about megavolts or picofarads. These are very large or very small quantities, and it's easy to express them if we have a common language. So we need an easy way to express these numbers, both verbally and mathematically. And the SI system specifies a system of prefixes for use as multipliers. So going back to the units, the SI system has only 7 base units. Now, these units are studied extensively and very accurately defined, and we'll talk about that in a minute. The units are the Kelvin, which is for temperature, the ampere, which is for current, the second, which is for time, the meter, which is for length or distance, the kilogram, which is for mass, the candela, which is for luminous intensity, and the mole for the amount of substance. Now, physicists will need to have a good appreciation of all of these, but in amateur radio, and in order to reduce the scope of this slide video, we'll just have a look at 4 of them. The ampere, the second, the meter, and the kilogram. Now, below the ampere there, you can see a little representation of what is called a Kibble balance. The definition of the ampere is currently based on the force between 2 infinitely long pieces of wire in a vacuum 1 meter apart. Now, obviously, in a national physical laboratory, it would be impossible to have 2 infinitely long pieces of wire parallel in a vacuum. So a device called a Kibble balance is used to measure exactly 1 ampere. And that is, if you like, the baseline calibration for the country that hosts that particular laboratory. The second is currently defined as a proportion of a day, and that is 1/86,400th of a day. And you can appreciate that there are problems with exactly defining this without uncertainty. It requires a lot of astronomical measurements, etc., to define what is exactly 1 mean day. So very difficult to reproduce that. The meter was originally 1/100 millionth of the distance between the equator and the pole. That was what it was meant to be based on, but recognizing that that is difficult to derive, the French constructed a standard meter which they keep in a safe in France, in Paris, and Other meters are produced for national physical laboratories based on that meter and sent off around the world, and they become the national standards for those respective countries. Similarly, the kilogram, originally it was meant to be the weight of water, a litre of water at about 4 degrees centigrade, that is when it's most dense. But recognising the difficulties there, the French machined a standard kilogram made of platinum iridium and keep that in France, from which other standards are derived and sent around the world. Now, the problem with these measurements is that they're difficult to derive and they suffer from uncertainties. And gradually, the standard kilograms that were located around the world started to diverge by apparently up to 50 micrograms or something like that, due to picking up of surface dirt, etc., and differences in the cleaning techniques between different countries. So a lot of the units that are derived from the fundamental units depend on the kilogram, for example, so it's a good idea not to have different kilograms in different places. So a move was set underway a few years ago, and by the 20th of May 2019, not long hence, the move will be complete, and these fundamental base units will be measured against fundamental physical constants, and so that will remove the variability. So, for example, the ampere will be defined as 6.24 times 10 to the 18th elementary charges per second passing a point. So for an ampere of electricity, it'll be 6.24 times 10 to the 18 electrons passing a point per second. Indeed, the second itself, instead of being part of a day, will become a very large number of periods of radiation of cesium-133, the atomic isotope. Now, this oscillates at a particular rate very accurately, and so that then it forms the new standard for measuring the second. The platinum iridium bar, which is exactly 1 meter long in Paris, the standard will now change to the distance that light travels in a vacuum in a very small fraction of a second, the fraction there shown on your screen. And you may note that we use 3 times 10 to the 8th meters per second, and you can see where that comes from. That's derives from that figure. And the kilogram, instead of the IPK, International Prototype Kilogram, located in Paris, there is a redefinition of what's called Planck's constant. Planck's constant is a very precise amount of energy, and used in quantum physics. It's used in the establishing the energy of a photon from its frequency. And that figure there that you see on your screen, you can see the dimensions of it are kilograms, meters, and seconds. Now, kilograms, you will notice, are the constant that the base unit we have in mind. Meters, you can see, are defined in terms of time, in seconds, and of course seconds is are determined in terms of seconds. So this interesting concept comes up here that the kilogram is now just determined in terms of time, which is something quite difficult to get your head around. But there we have it. So the basic message here is that whereas before we had prototypes from which measurements were taken, or we had astronomical observations, or we required a Kibble balance to determine the quantities for these for the old definitions. Now that's all taken away, and the base units are now defined by fundamental physical constants. So let's have a look at some of the derived units, and we only have a few. We only use a few in amateur radio. Here we have the 4 base units, and one of the easiest, of course, is the hertz, the unit of frequency. And if we know what a second is, and if we count the number of oscillations in 1 second, then we've got the hertz. So the unit for that is 1 over seconds, or seconds to the minus 1. If we look at the Newton, the unit of force, meters, kilograms, second squared, there we have seconds, meters, and kilograms. So there is one of the very important derived units. Not so important for us in amateur radio directly, but important in as much as it leads on to further derived units. Further to that, we have the joules, newtons per meter, so that the Newton then feeds into the joule, and the watt, which we do use extensively when measuring power, is 1 joule per second. So you can see that the second then feeds into the watt, and so does the joule, and the joule has in turn come from the Newton. We can also see here coulombs. A coulomb is that very large number of electrons that we saw before, and that's 1 amp per second is 1 coulomb. We can now see the volt in terms of watts and amps. So that's watts divided by amps. And we can see, for example, the farad, C over V. So that is coulombs, the amount of charge, over the volts. So with all of those, finally the ohm, volts over amps, you probably recognize that from Ohm's law. That takes the volt from the bottom and the amp from the base units, and you can see the general pattern by which the derived units build out of those base units. The 7 base units, but only the 4 that we need to consider here. So here are the 22, the full 22 derived units, of which a lot of them are completely outside the scope of anything we do, and perhaps those that are highlighted are mainly the ones that we are concerned with. Although you could argue, for example, that the Siemens or the Tesla or other units were also important, but we don't want to get too involved in that. Now, we've talked about multipliers a little bit. If we saw a road and the road had a sign and it said Paris 200 kilometers, we would understand from that that it was 200,000 meters. We would understand that the K was representing 1,000. So we would expect to see or have to travel 200,000 meters to get to Paris. Similarly, if we measured a pencil at, say, 3 centimeters against a ruler, we would understand that that was 3/100ths of a meter, and that it was the cm, the centi part, that told us to divide by 100. So in our everyday life, we're already using SI to accomplish tasks. So here then is a list of multipliers. Now this is a partial list, and for the advanced course you don't need to know any more than these. There are greater quantities, i.e. quantities that are multipliers that are greater than tera, and there are smaller quantities than pico. And of course you can look those up on the internet, and if you're interested, but to be honest, they're hardly ever used. So engineers tend to prefer powers of 3 for the multipliers. You can see there, for example, hecto and deca, and you can see that the multiplier is 10 squared and 10 to the 1. So, for example, a decameter is 10 meters, and a hectometer is 100 meters, and a kilometer is 1,000 meters. And you won't hear engineers talk in terms of hecto or deca. Similarly, you won't hear them often talk in terms of deci and centi. So, apart from those 4, you will notice that all of the powers there are multiples of 3. In other words, 10 to the 3, 10 to the 6, 10 to the 9, 10 to the 12, and on the smaller than 1 side, 10 to the minus 3, 10 to the minus 6, 10 to the minus 9, and 10 to the minus 12. So we can largely ignore hecto, deca, deci, and centi. The only exception to that is that for centimeters. For example, we do talk in amateur radio about the 70 centimeters band. We're talking about a wavelength of 70 centimeters, so in a way perhaps we ought to retain that one. But apart from centimeters, we hardly ever use it, and I think we're probably au fait enough with centimeters to strike it from the list for the time being. So if that's the case, this would be the engineer's list. And these are all of the prefixes and multipliers that and symbols for them that you need to know right up to the advanced course. So bigger than 1, kilo, is 1,000, mega is 1,000,000, giga is 1,000 million, and tera is 1,000,000 million. And smaller than 1, smaller than unity, milli is 1,000th, micro is 1,000,000th, nano is 1,000 millionth, and pico is 1,000,000 millionth. And you can see there the multipliers, the powers of 10. What do we mean by a power of 10? Well, they're all written 10 squared, 10 3, 10 to the 4, or whatever. If we're talking in multiples of 3, 10 to the 6, 10 to the 9, etc. Now these powers of 10, if you like, 10 to the n tells us how many times to multiply 10 by itself. So, for example, we might have 10 to the 3. And 10 to the 3 would be 10 times 10 times 10. In other words, 3 times. And that would be 1,000. And if we have a look at the list there, yes, that makes sense. We know that kilo, 1 kilovolt is 1,000 volts. And we would start to get au fait with the fact that that's 10 to the 3 volts. If we're looking at quantities of less than 1, then it would be 10 to the minus n, and if the minus sign is there, we divide instead. So, for example, 10 to the minus 3 would be 1 over 10 times 10 times 10. In other words, 1 over 1,000. And what do we see there? We see that that would be milli. So 10 to the minus 3 is synonymous with milli, and we should know the symbol there, m. Now it's worth bearing in mind here that all of the quantities greater than 1, apart from kilo, use a capital, and all of the quantities less than 1 use a small lowercase letter. Incidentally, when you're looking at the units, if you want to know whether it's a capital or not, if it's somebody's name, like Kelvin, for Lord Kelvin, it's a capital K. If it's S for second, which isn't somebody's name, then it is a small s for second. So Ampere was a person, and so he gets a capital A. Kelvin gets a capital K. S gets a small, second rather gets a small s because it's a unit of time. And kilogram gets a small kg because it's not somebody's name. So that's the rule there on capitalization. When we're going back to powers of 10, you should also remember that 10 to the 0 is always 1. In fact, anything to to the power 0 is 1, 2 to the 0, a million to the 0, but certainly 10 to the 0 is always 1. So if you look at the units there, unity there, 10 to the 0. So for example, to say 1 volt, I can say 1 V, or I can say 1 times 10 to the 0 V. It's the same thing. Excuse me. Let's do some arithmetic. Let's say we had a simple circuit with 2 kilovolts driving 800 milliamps around a circuit through a resistor. And from the base units there, we know that the derived units, I beg your pardon, the ohms are volts over amps. And we know this from Ohm's law, R equals V over I. And in this case, it would be 2 kilovolts over 800 milliamps. Now, how would we write that? We'd write it like this: 2 times 10 to the 3 over 800 times 10 to the minus 3. And we would put that into the calculator in engineering notation, and or standard form, it's sometimes called, and the answer would come up as 2.5 times 10 to the 6, or 2.5 mega ohms. Now, to actually perform this calculation, you will see some videos on the Texas Instrument TI-30XA. I think there are 3 in that series, and they give you a good guide on how to put stuff into the calculator using the SI multipliers, or standard form. Right, now that all seems fairly straightforward. There is a problem with mass and the kilogram, and it becomes a bit messy. And this is for historical reasons. For example, you can rightly say that 1,000 volts is a kilovolt, and that 1/1,000,000th of a farad is a microfarad, and that's fine. But because the old fundamental unit was the gram, that's predated the kilogram becoming, if you like, the base unit, the kilogram already has kilo in it, in its name, and the abbreviation kg. So you can't say 1,000 kilograms is 1,000 kilograms, or kkg. I mean, you can say it, but it's a bit cumbersome. And you can't say 1,000th of a kilogram is 1 millikilogram. It doesn't make any sense. 1,000 of a kilogram is a gram. So the main thing there is not to worry about it too much. Just remember that the base unit is the kilogram and not the gram. So this is got around by saying 1,000 kilograms is a ton, or a metric ton, and 1,000th of a kilogram is simply a gram. So there we have it. That's a quick run through SI units. There's plenty more online about that, as you can imagine. Once again, don't panic. It's not something you have to understand in detail, and this is only to give you an appreciation. Thank you very much for listening.